In our calculus journey, we're going to look at stationary points. We're going to learn what they are, and we're going to classify nature of stationary points, i.e. the types there are, and an application. So first of all, we can see a generic graph here on the left, and you can see it's labeled already for you, and we've got a restricted domain from A through to B. In there we've got 4 key points that are labeled. Okay, this one's called a global min. This one's labeled global max, local min, and global max. So there's global and local, and there's max and min. The max and min are short for maxima, maximum, and minimum. So that probably isn't a big shock to you. Minimum. Now, local, if you look at this local minimum compared to the global minimum, the global minimum hangs down even lower than the local one does. Same thing with the local and global maxima. So this one here, in this vicinity, this is the highest point along the y-axis, and this one is the lowest point in a vicinity. There might be other ones. So a local maximum is the highest point within a restricted domain or a region. Local minimum is the lowest point in a restricted area or a region of the graph. And a global max would be the highest point in total within the allowable extent of the graph. And this one only goes up to B. And that's the highest of all. And minimum, the global minimum, is the lowest of all. Now these maxima and minima, the highest and lowest points, sometimes are called turning points, so you need to be aware of that. So we have maxima, minima, and turning points, and those are the first 2 types of stationary points. What makes a stationary point what it is? Well, basically it's when the gradient equals 0. Now if you have a look at these ones here, if you took a tangent there at that maximum, it would be horizontal, i.e. the gradient of the tangent is 0, therefore the gradient at that particular point on the graph is 0. Same with this local minimum here. It's not necessarily the case with the global ones. That might just be where the graph gets cut off, and as you can see, the gradient certainly is not 0 there or there. But at the local ones it is, and at the turning points it is. So the turning points are one type of stationary point. Okay, and some people link that word stationary to it's not climbing. For a moment, it's not climbing or not falling. It's got a 0 gradient. Now if the gradient equals 0, the derivative at that point equals 0. So to get a maximum stationary point, you have to have a positive gradient just prior to the maximum, and you have to have a negative gradient just after that stationary point. So if we have a positive 0 and negative, we get that shape, just like that shape there. So if the gradient is positive just before the turning point, that means the derivative dy dx is positive as well. And if the gradient is negative afterwards, dy dx would be negative afterwards. And of course, at the turning point, dy dx equals 0. The opposite is true for a minimum. So that's for your local minimum. We have a negative gradient or a negative derivative, a 0 value for the derivative or 0 gradient, and then positive. So negative, 0, positive makes a minimum. So those are called stationary points, those 2, and they're turning points. There's another one. Now this one's been put in table form. Now if we have a negative, then a 0, then a negative, that might go like that. Sorry, it might go like that, and then that. Or it might go like this, then that, then this. So they're called points of inflection, horizontal inflection. So a negative, 0, and then a positive will be like that one there. That's an inflection point, and that's also the other sort of horizontal inflection. So occasionally you get those. So they're not turning points, okay, but they are still stationary points. So inflection points are stationary points. Let's look at an example where we can use this idea. From a square piece of metal, so that's my drawing of it there, and it has a side length of 2 meters. So it's 2 meters each way, being a square. 4 squares are removed as shown in the diagram. I'll show them now. So we have, well, that's not a square. Try again. And it would make a crease along like that. And we have another square removed there. And another crease along here. And likewise. So we have 4 identical squares removed from each corner. And you can see that, perhaps you can see that you could fold these sides up here, all 4 sides, and you would have like a tray, okay, or an open box. That would mean that this would form, once the sides are folded up, that would form the bottom or the base, and these green zones would be all folded up, and they would make the sides, and the bits here in yellow are the bits that are removed. Okay, does that make sense? I just need to put in my last green one there that I didn't put in. There we go. Our job is to find the value of x. Now x is the little side length of the squares that are removed. That's x. All of these little things here would be x. Okay, that would be another x there, and so on. All those little side lengths of the squares removed. So we have a big square, 4 little squares removed. So what we've got to do is find the value of x that gives the box its maximum value. Perhaps you've done this in younger grades using trial and error, or even more advanced trial and error for spreadsheet or something, but we're going to use calculus, and we're going to exploit stationary points to help us. Show that the volume for this is a maximum for this value. So the maximum volume. Okay, so volume of, what's this shape? It's an open box, so it's a rectangular prism. It's length by width by height. Now we don't have such things, we have x basically, v and x. So we're going to come up with a v of x formula. Now I'm going to hereby say that this, even though it's a square, that's going to be called L, and across the bottom there that's going to be called W, even though they'll be the same, and basically the height will be this bit that gets folded up. What you might need to do is get a piece of cardboard and try it yourself if you can't visualize this. So the length is going to be 2 meters minus 2 lots of x. The width is the same, so that the length is 2 minus 2x because you're minusing an x off each side, and the width is exactly the same because it's a square, so that'd be 2 minus x times 2 minus x. So that'd be 2 minus x all squared. The height is this amount. Now that's x, isn't it? So it's going to be times by x. So we have an a minus b in the brackets. A minus b all squared is a squared minus 2 times a times b. So that's 2 by 2 is 4 by 2 is 8, 8x plus b squared, which is 4x squared, all times by x, and we have 4x minus 8x squared plus 4x cubed. That's essentially our volume function. I'm just going to put it in order with the leading term first, the 4x cubed. I'm not changing it, I'm just putting in the term of the highest power first and just putting it in order. So that's v of x. So what we have to do now, the maximum is when the derivative is equal to 0. So what we do is got to find v dash of x there, the derivative of that. So that's 12x squared minus 16x plus 4. Now, the stationary point means v dash of x equals 0. So 0 equals 12x squared minus 16x plus 4. I can divide all terms by 4, so that would be 3x squared minus 4x plus 1 equals 0. We need to solve that quadratic. Okay, so I quickly factorised that and I've solved it using the null factor law. So x has got two values, 1/3 or 1. Now we do need to check the validity of these. Now if we go back to our volume there, if we use 1, we've got a problem there. In fact, if we go to the expression for the length, which is 2 minus 2x, it doesn't have to be the length, but I'm just choosing that. 2 minus 2x, I should say. 2 minus 2x. Let's get rid of that there. 2 minus 2x. If you make x equal to 1, Houston, we have a problem, because that is a turning point, a stationary point, but it may not be a maximum necessarily. And in fact, if we just sub those values in, that will give a length of 0. So when we cut a square out of size 1, we've actually chewed up the whole length. In fact, that makes sense, doesn't it? Because the entire length is 2, and then if we take in 1 from each end, we're going to meet in the middle. That'll be the minimum volume, i.e. 0. Now that's useless to us. All right, let's try the other one. X equals a half. X equals a third, I should say. So we'll try that, and what do we get? Yes, so 2 minus 2/3, which is okay. So x equals a half is the a third. I keep saying a half. X equals a third is the answer. To test whether it is a max, we need to do a little table, and what you do is look at, just like we looked at earlier, that's at the stationary point, and then we need to look at a value just before and just after. Now if x is a third is where our maximum seems to be, we need a value a little bit, I would go for a value a little bit less than a third. Now 0.3, you don't have to choose 0.3, but it's near a third and it's a little bit less. And then 0.5 or a half, sub that in to the function v of x, v dash of x I should say. So because we're looking at the gradient, so you need to substitute it into the derivative. And to keep the video short, I haven't shown those calculations, but if you sub a number a little bit less than a third in, you get a positive value for the gradient, and a little bit bigger than, you get basically a negative value. That shows that it's a maximum.